So the last subject within this chapter of topology is a very important thing called compactness. Now, I could spend months talking about why compactness is important. Unfortunately, we don't have this time, but I will give you the abstract definition of compactness, tell you how you can use it to prove many other things, and I hope you find this interesting. It is something that is mentioned in many other subjects of mathematics, not just real analysis, 337. It will not just be useful for that, but for many other things. You can think of compactness in very simple terms as a means to deriving something finite when you know that something infinite happens. So for every infinite theorem or infinite something that is true about an infinite structure, you may be able to derive some finite counterpart. And that is what compactness is in a nutshell. Now, why do we need to introduce this as a subject? You might be thinking, can't we just take any finite chunk of something infinite and then we're done? The thing is, if we want certain properties to be preserved, we may not know how to cut this finite piece of something infinite. For example, if you have a list of numbers and this list is infinite, and you have some property that you know this list satisfies, it may not be enough to just take the first 100 numbers. You may need to do something a lot more complicated to find a finite set that has the same property, whatever it is we're thinking about. So let me just tell you what the compactness is. We're going to prove some very simple exercises. And in the last lecture about this chapter, which is this Thursday, I will prove to you, I think it's 2 or 3 theorems that are equivalent to the completeness of the real numbers, which will tell you why the completeness of the real numbers can be thought of completely in topological terms. You don't need any metric, you don't need algebra, you don't need anything like that necessarily to talk about it. This all makes sense in the language of topology. It is just a property of shape, not necessarily about sequences and not necessarily about the order, although that also makes sense. So that I don't just ramble the entire class, let me start writing down some ideas. So first, before I define compactness, we need one auxiliary definition, which I think you will find quite intuitive based on everything we've done. So let A be your favorite set in the space that we're thinking about, Rn, mostly for the real numbers, but we can define this more generally in Rn. So take a subset, a family. Family is a synonym of set, right? Just that when I'm talking about a set of sets, it sounds better to say family. So a family of open sets of Rn is called, and this is the definition, this is the word I'm defining. Let me call this family F, because why not? Family F of open sets of Rn is called an open cover, right? The definition, this concept has those 2 words, open cover. And if you're reading Royden's book that contains this definition, maybe slightly in different terms, there's an explanation why this notation is actually pretty bad. Calling this an open cover is not ideal, but I don't want to get into that because it's not really important right now. It's called an open cover if the only thing we need an open cover to satisfy is that every element has to be in open sets, right? We are just talking about open sets, and they need to cover A, meaning if I take the union if I take the union of all these elements, then A is contained there, right? It doesn't have to be equal because that would mean that A is open. I don't know if A is open, but this is an open cover. So let me give you some examples and some non-examples, right? The concept or the intuitive idea of covering something should be very clear. So let's start with a drawing in R2. If you have a set that looks like this, maybe I can make it a bit rougher. This is a set, right? In the plane, this is a subset. How can I cover this with open sets? Well, a cover is anything that consists of open sets and that covers the entire shape, right? It doesn't leave anything outside. Now, it may cover more things. It doesn't have to be equal. But the important thing is that the set A, maybe I should have used different colors. Okay, and there's a question in the chat. Okay, so Bill is saying in the chat that it's a bad name exactly because of that. The adjective open does not decorate cover, but it means covered by open sets. Yes, that's exactly right. Um, so we will eventually talk about finite families, and we will call those finite families that are also open covers, finite open covers. But finite decorates cover, meaning that the set F is finite. But open doesn't decorate cover because open refers to the elements inside the cover, right? The cover is a family of sets. It doesn't make sense to talk about whether it's open or not. So it's not the cover that is open, it's the elements inside the cover that are open. That's why it's a bad name. Yeah. Yeah, I find that funny too, but it's not that crucial, right? But yeah, thank you for adding that. I actually didn't quite remember what it was exactly, but it's exactly that. So this is the set A, and then a cover is, anything that just covers the entire thing. It leaves no gaps. This is F, right? So this is an open cover. Okay, so maybe let's write down a more concrete example. So this was example one, just a drawing. Example two, what are open covers? So one example of a set is R2, right? R2 is an example of a subset of R2. What could be covers, open covers of R2? How can you cover the entire plane? Can you cover the entire plane? There's many ways, right? There's many, many ways, but there's two that I have in mind. For example, you could do something like this, right? Where you take integer coordinates, right? And why don't we just write this down? So an open cover would be you take balls that are centered around n comma m of radius. I don't really want to do the math right now, so let's just say radius 10. I know you could make the radii smaller, but 10 works, right? So whatever. N and m are integers, right? And this is an open cover because each open ball is an open set. We mentioned that, maybe didn't really prove it very explicitly, but I did tell you how to prove it. And it covers every point, right? Every point is in some of these balls, even those points that aren't integer coefficients, right? The point pi comma 2 is inside the ball centered around, hopefully I get this right, but it must be inside this one, right? 3 comma 2 or radius 10, it's definitely in there. Okay, so I have there's a question in the chat. Would the open cover be trivial because R2 is open and it is covered by itself? Yes, yes, R2 is covered by, an open cover can consist of just one element. So that is true. There's an open cover that is trivial. That's actually a good example. So let me erase this because this isn't that important. This is an open cover. And it's a countable open cover, right? You can also find uncountable ones if you center these balls around every possible point. Is an open cover. As it was mentioned in the chat, if I just take R2 alone, well, this is an open cover, which is kind of boring, right? Is an open cover. That's a good example. Maybe one more example. What if instead of, so in the first example, the radius is fixed, but the centers are moving. So in the last example, why don't I just do the opposite? Let me fix all of these in the center, but now the radius is moving, right? Now n is allowed to vary. Natural number. This is also an open cover, and this looks like this, right? First radius 1, I mean radius 0 is the empty ball, that doesn't matter. Radius 1, radius 2, radius 3. So this is this one, and this is this one, right? Is an open cover. Okay, so that's the idea of an open cover. Okay, followed by the previous question, do we have different names for covers that are all members are bounded versus unbounded? I don't think so. I mean, Yeah, I understand the question, but I don't think we make that distinction between covers that are bounded or unbounded. But that's actually a good point to bring up because the next definition I want to write down is exactly that. Right? So a set of real numbers, let's say a subset of Rn is bounded if if it is contained in some open ball or some ball, right? And unbounded otherwise. I'm not going to write that down because I think it's clear from context. Okay, so what is an example of a bounded set? By the way I defined open balls, which might be different from the way other people define it, radii are always finite. So the R2 is itself not a ball, right? Even though some people might consider it that, which is fine. So let me give you some examples. What kind of sets are bounded? Well, balls are obviously bounded, right? Open balls, because they are contained in themselves, are bounded. Maybe something that is not too hard to believe is that Rn is unbounded, right? You cannot cover Rn with just one ball, right? You would need multiple balls, like I did up here. But there's no ball that's large enough that will cover the entire space because every ball is bounded, it's finite, right? Another example, I don't know, let's just make a sketch, something that is bounded. Maybe I'm too many examples, right? So this set is bounded because you can enclose it within a circle. Anything that you can enclose within a circle is bounded, and anything that you cannot encircle in this way is unbounded, right? I think this is pretty intuitive. Are there any questions with this so far, or does this make sense? This is all we need to define compactness. But as you will discover in a minute, compactness is actually kind of tricky. And there's many ways of defining compactness. I will give you the more abstract definition, not because I'm doing you a disfavor, but because this will connect very nicely with every other type of compactness you will ever see, right? This is the more general way of seeing this, and there are advantages to seeing this in a more abstract way. I will obviously also tell you how to connect this with more familiar definitions like those involving sequences, which in my opinion aren't really simpler. It's just that you've talked about sequences more. Okay, so now we are ready to write the main definition and the last concept that we will mention in this chapter. And there's only one more chapter left in this course. So a set, what should we call it? K is called compact if what? Every, and this might seem a bit absurd or nonsensical. I will explain this in a second. Every open cover of this set, of course, contains a finite open cover. So an open cover is a family of sets. So it makes sense to consider the case when this family of sets is finite. This definition is telling you something is compact if no matter how you cover it with open sets, you can always just extract finitely many that still cover the set, right? No matter how you cover it, how contrived you construct this family of open sets, you only ever needed finitely many, right? I can easily give you examples of sets that are not compact. So examples. So Rn, which is the total set, the space, is not compact. And I can easily prove to you that it is not compact. To prove that something is compact, you need to show that every open cover has a finite open cover. To prove that something is not compact, I have to give you one open cover that contains no finite open covers. I know this might seem a bit abstract the first time you see it, but showing that Rn is not compact is actually not that difficult. Can anyone tell me what open cover of Rn contains no finite subcover? Okay. Okay, so someone already answered this in the chat. Okay, so Bill is suggesting what is essentially the third example that I saw here, right? So for R2, the third example are these concentric circles. This is an open cover, and it's an infinite open cover because there's infinitely many open circles. No finite amount of them will ever cover Rn because actually any finite amount of them just covers the biggest of the circles, right? The union of any finite amount of circles is the biggest of them, right? So in the end, it's just one circle. The same thing happens for the first cover, right? The first open cover that you can see on my screen is an open cover that contains no finite subcovers, because if I only take a finite amount of circles, I'm not covering the entire plane, right? I need all of them. I need infinitely many of them, right? The second example, the one in the middle, the one that's trivial, where R2 is the one covering itself, that one is already finite. So that one will actually contain finite covers. It's itself already a finite open cover. So this doesn't mean that every open cover doesn't contain a finite subcover. We only need to find one. So the proof, as suggested in the chat, is the open cover. The open cover, the one that we previously mentioned. Maybe let's just write it down one more time. 0, 0, n, where n is allowed to be any natural number, has no finite subcovers, right? Any contains no, does not contain, maybe. Wait, sorry. Does not. Finite subcovers. Okay, so this is an example of something that is not compact. And you can clearly see that very, very large sets that are unbounded, cannot possibly be compact for this reason, right? Actually, why don't we generalize this a bit more? This isn't just about Rn. And by the way, this is R2 because the cover I wrote down has only 2 coordinates right here, right? So this only works for R2. Okay, so here's, we can call this a proposition. I think it's simple enough. Compact sets are bounded. Compact sets are always bounded. Now, who can tell me why this is true? And it's the same proof, right? The exact same proof that we just did for Rn, pretty much the same idea works. I'm having some trouble writing stuff down with this pen. Okay, so any ideas? How do you prove that compact sets are always bounded? Weird. Any suggestions? Okay, so someone is suggesting contradiction in the chat. Okay, so contradiction, I like that. So contrapositive would mean that if something is unbounded, then it cannot be compact. And that's what we proved here for R2. We kind of used the fact that R2 is unbounded. It's too big to be contained in just one ball, right? Okay, so if a set is unbounded and you take this cover right here, The same cover works, right? That open cover, that one is an open cover of any set because it covers the entire plane, it covers the entire space. So in particular, it must be an open cover of your unbounded set. Now, if it were compact, you could cover it with just finitely many. But like I said, the union of finitely many of them is a circle, is itself a ball. And that's not true, right? Because it would contradict the fact that it is bounded. So let us write this down if my pen allows, hopefully. So suppose, okay, seems to have corrected itself. No. Suppose that K, let me try something. Okay, suppose that K is compact, but unbounded, right? Then this cover, then this, the same thing. Okay, let's do this proof in R2 just so that we don't have to rewrite this thing. You know what? I don't like these arrows. So let's do this properly. The balls centered around the origin of arbitrary size is an open cover. It's actually an open cover of everything, right? So in particular, okay, right? By compactness, there is a finite amount of balls that cover K because it's compact, and that's what the definition says. By compactness, there is finite amount, let's just write it down, B1, B2, all the way to BK inside this cover, right? Call it F, inside F, such that K is covered by this amount, right? So we take these balls, they cover. But this union, because they're concentric circles, if I take the union of any finite amount of them, they're contained in each other. So the union will absorb all of them. It will only give me the biggest one, right? So this will be some BL. Or some L, which would be the biggest one. But this contradicts, actually, I don't even have to write it by contradiction, right? I can just write it like this. Then K is bounded. K is bounded because K is contained in a ball. Not just any ball, but it is actually contained in one of these balls. One of these, but I don't really care about that. So it's contained in a ball of natural radius, of a radius where, well, the radius is a natural number. Okay, so that was easy. We know that compact sets are bounded, so any unbounded set is unfit to be this. There's another property that we can easily prove, hopefully, about compact sets. So here's property 2. Property, maybe let's label them, why not? Property 2. Compact sets are closed sets. Now this might be less obvious than the fact that they are bounded. How do you prove that if something is compact, then it has to be closed? Actually, we can prove something slightly stronger and save a step now that I think about it. So let me rewrite this in a way that will be stronger. So I will not just prove to you that compact sets are closed. Wait, give me a second. Actually, it's fine. It's fine. Let's do this and we can generalize it later because the proof won't work now that I think about it. Okay, let's prove this. So how do you show that compact sets are always closed? Why do they need to be closed? To use the fact that a set is compact, so let K be compact, we need to suggest some open cover, extract a finite open cover, and that will somehow give us some information, right? So how do we do that? Any suggestions? This is actually a good exercise. Now let me go ahead and spoil the future, the rest of this chapter for you. What I want to prove is that it is easy to show that compact sets are closed and bounded. What is not so easy to show is that the other direction is also true. Closed and bounded sets are also compact with this definition. Now, this might seem weird because you will say closed and bounded is so much easier to think about than this weird definition with open covers. So why did I bother defining it the weird way if the first thing I'm going to do is prove to you that they are equivalent? But there's a reason for that, and the reason is that you will use these covers for many other things because every single thing about compactness can be proved using these covers, and many consequences of compactness are much easier to deal with when we are thinking about them in these terms of covers. So even though the definition is more difficult to understand, it is easier to work with than closed and bounded. But you're gonna have to trust me with that because I cannot show you this within 10 minutes, right? Okay, so how do we show this? And there's one more property that I think is important. And notice, by the way, I haven't given you a single example of a compact set. I gave you some examples of sets that are not compact. Now I have two properties that can be used to show that many sets are non-compact. But one question you should have for me is, can you give us an example of a compact set? And this is actually more difficult than it might seem. Okay, so in the chat, I'm getting some suggestions. We can argue that the union on finally many sets is finite. Okay, okay. Yes, we have to use something like that. But how do we achieve the closeness part, right? We have to use properties of closed sets. Let me write down the next property so that you can think about more than one thing at the same time in case you want to, in case you get ideas for something else as well. So if K is compact and C is closed, then actually C is compact as well. So every closed subset of a compact set has to be compact as well. That is easy if we already know the theorem that compact sets, if and only if closed and bounded, because every subset of a bounded set is smaller, so it has to be bounded as well, right? But this is actually a crucial step in what we're going to use, so maybe I should call this lemma rather than proposition property. Lemma. This is also a very short proof. Okay, so here's one suggestion that we can use contradiction. What happens if it's not closed and then use the definition of compactness to get a contradiction? Okay, sure. Let me give you a minute or two to think about the lemma as well. The lemma has a bit of a more pure proof. Let me maybe can do a sketch of how this would work. Right. So the thing this is saying is compact sets kind of look like this, right? They're kind of like closed and bounded sets. The idea is that if you have something that is already closed, but it is also contained in K, then that has to be compact as well. Now, how do we use this covering property? Because we don't know anything else about compact sets. We don't even have an example of a compact set, even though that is the next thing I want to prove to you. The first example of a compact set. So any suggestions? What what open cover would be useful for what I'm trying to prove up here, right? We need to define an open cover, and then using a finite subcover of that, like a finite cover contained there, we have to conclude that this is a closed set. Any suggestions for either of these? What open cover can we use? And I like these two proofs because they're very pure, right? They don't require any knowledge about the real numbers, about Rn, about anything. These are pure topological proofs that only use the definition. So what open cover would you suggest for either of these? I think the first one is actually not the easiest. Okay, so in the chat, I'm getting some suggestions. So I like that idea, right? Every boundary point, and you find open covers that approach it. Yes, that's the right intuition to have. It's like you're zooming in, but in the end, you only need finitely many of these open balls that cover each point. Yes. Okay. Yeah, I like that intuition. So I think we can start with that. Let me see. I'm trying to open something in my computer, but I'm being unsuccessful in it, so I will just have to cite it. Maybe I can write it up here. So let me just move this down. So it is the right intuition to have, but there's a slightly easier way of writing it that doesn't involve approaching points or boundary points, but it is the correct thing to think about. So recall, and by this point, I think you should all know how to prove this because it's, I think, the first exercise in the problem set. By problem set 5, I think it's number 1. C is closed. A set is closed if and only if its complement is open. And conversely, a set is open if and only if its complement is closed, right? So we will use this because it's usually easier to show that the complement is open rather than showing it directly, right? So we show it is enough to show that if I take Rn and I remove K from it, this is an open set, right? The definition is just a bit gentler in this case. So knowing that this is open, we already have an open set. So what other thing could we do? All we have to do is find some radius for every point in there that is still contained in it, right? That's what it means to be open. So let's pick a point, x, inside this set. And then what? Okay, let me do a sketch because this is actually slightly more difficult than the one below it. So here's the idea. Here's x. X is something that is outside of K, right? So instead of approaching each point in K, which would give you the correct solution, and we can rewrite that using the suggestion I got in the chat as well. Something that works in this context is I want to isolate each point of X from each point Y inside the set. Why do I want to do that? Well, because I want to cover K somehow and then use the fact that this cover only required finitely many elements. So X and Y are different points. right? So we can definitely isolate them like this. And if I do that for every point in K, let's say that okay, maybe I need to draw this a little better. So points that are far away, I may only require a really large open set, or sorry, a really large ball that doesn't contain X. So this is Y prime, right? This radius can be large because it's far away. Those points that are close to X though, let's say X is not too far from the border, from the boundary, then I need a smaller radius, right? But the point is, I can do that for every point, right? For every point. So for each point Y inside K, fix disjoint. How do we pick them disjoint? We'll just measure the distance between them and do the radius 1/2, like half the radius, half the distance, right? Fix disjoint open balls. Open balls, oh, sorry. B by 1, b2, y. It depends on y, right? For different points, I need different different balls. So this would be b2 y prime, and maybe this one, which might intersect k, we don't really care, is b1, sorry, b1 y prime, right? So we fix two disjoint open balls, and then the collection of all of these must cover K, because we're doing this for every point. So it's not just an open cover, but actually every point is not just being covered by an open set, it's actually the center of one of these balls, because I'm picking all of them, right? Then the set of all of these by's, sorry, that's not the way I wrote it, it's b2y. Okay, is an open cover. It's open cover because, well, all of these are balls, and it covers because Y is at the center of each of these, right? So this must be an open cover. So by compactness, pick B, running out of indices here. Let's just remove the index. I don't think we really need it. Open balls, B prime, right? Okay, so the indices could be something like B1 for different points, right? B2, B3, they were picked out of different points. So we have all of these balls. And each of these balls does not contain X, because X is the fixed point from which we determined all of these things. Sorry, this should be an N, not 4N. But these still cover, okay, open cover of K, right? So now what do we do? Now what do we do? We know that this is a finite cover, and none of these contain X, but now we use the counterparts, you know, the twinning parts of these. So now what do we do? Any questions with this so far? I know this might seem a little bit abstract, but let me know if the intuitive idea makes sense. Some people in the chat already commented on this, and they have the right idea. Okay. Yes. Okay. Let me make a bigger diagram, and maybe this will make more sense that way. So here's the idea in a nutshell. Why do I need these covers? I'm not actually going to use the ones covering K. I'm going to use the other ones, right? Because I want to figure out what is happening with the complement. Okay, so let me make a better diagram of this. Okay. So what is happening is I have this set K and I have a point X. What I want to achieve is some ball that is still outside of X. I need some radius or some open set that contains X that is disjoint from K, because then I would have proven that the complement of K is an open set, right? So this ball must be small enough so that it is completely isolated from K. It is completely separate from K. Now, I don't know how to do that, but I know how to do that pointwise. And this is exactly what I mean when I say that it is an infinite property that compactness translates into something finite. Because I don't know how to isolate X completely from K, that's what I want to prove. But I do know how to isolate it from each point of K. But K has infinitely many points, or could have infinitely many points. So I have to translate this to a finite property. So the idea is as follows. Let me draw this a little closer maybe. So this is y and this is x. These two can be separated. Just pick half the distance between them as radius and you have it, right? Of course, if I want to make a better drawing, I should make things a lot closer so that you can see why this is complicated. Sorry, x should be closer, y should be further away. Okay, so let's isolate these, and as you can see, if I do this for just one point, then x is the ball that I found for x is still not disjoint from k. I have to make it smaller. But if I isolate it from every single point individually, then this will give me many, many, many circles, right? One pair for each of these points. I know that K is compact, so I didn't really need infinitely many circles to cover K, only finitely many. Maybe the ones that I'm drawing here, right? Now, why could this be complicated? You would think that of all the balls that are covering X, I need to take the smallest one, because that one will isolate it from every point in K. But what is the smallest one? If there's infinitely many circles, then this doesn't make any sense. Also, I cannot intersect them, because the intersection might not longer be an open set. Now, the conclusion that is missing is that if I only have finitely many open sets, then the intersection is indeed open, and I can conclude the argument the way I intended. So actually, why don't we do that? And then I will give you enough time to think about this, and we can leave this lemma for next time. Okay, there we go. Let me see. Okay, perfect. Right. So the idea is we want to intersect all of these open sets that are covering X to make it as small as possible and isolate it from K. But if this isn't open, it might just be the point X, as you saw in the previous tutorial. That could happen, right? Some open sets are like that. So infinity is very bad when we want to intersect open sets. But luckily, because of compactness, we already have a finite amount. So why don't we just do that? So X is in the intersection of all of these, what did I call them? The ones covering, maybe I should have written this a little better. So X is contained here and Y is contained here, right? So the ones that are covering Y are the ones that have a prime up here, right? So this was I. This is an open set. Now this is an open set because it's the intersection of finitely many open sets, right? Containing what is it containing? Contain X. So I claim, what do we want to call it? Call it U. I claim that U is not just any open set that contains X, but U is actually disjoint from K. And why is this true? If not, if this weren't true, then suppose that they do share a point. There's a point Y that is in U, but also in K, right? But then pick I such that Y is contained in B, Y, I. It doesn't have to be the same point, right? But recall that this is an open cover. Let me underline this. So this finite amount is an open cover of K. If it's a cover of K, then one of them must contain this element Y because it's just a point of K. So it must be in some of them, right? In at least one of them. So let's say it's in this one. But B yi is disjoint from B prime yi because that's how I picked them, right? I picked all of these balls with the same point to be disjoint. And this is a contradiction. Why is this a contradiction? Well, because y is contained here. And sorry, not, did I pick the right indices? Of course I did. Okay, so this is x. Wait, let me just double check this. Yeah, x is in the one with the prime. And this is impossible, right? This is impossible. So these cannot overlap. So then Rn minus k is open. Thus, k is closed. And I just proved that compact sets are closed. Now, unfortunately, we are running out of time, so I will not obviously try to prove this lemma right now. Let me know if you have any questions. I will stay here until the end of the lecture. Stop the recording for now. Actually, let's keep it going in case there's questions. And next Thursday, I will finish this topic. And don't worry, this doesn't play a huge role in the problem set, maybe only for the additional exercises, but nothing beyond that. And I will tell you how this is connected and give you some exercises so you can practice this for both the final exam and for MAT 337 or similar courses that use this important concept. So let me know if anything is unclear, and I will do my best to clarify it either now or on Thursday. And I hope you have a nice week in case you don't have questions. Yes. Okay, someone's asking in the chat about next Thursday. The Thursday is a normal lecture. Yes, Thursday is a normal lecture. Or is there any reason why it shouldn't be a normal lecture? Yeah, you're welcome. Okay, so what is a close? Someone's asking, what is a closed set in this course? Right. So let me answer that. Closed set is one that is equal to its closure, and this is defined right here. Right? If you look at the bottom of the page, somewhere, yeah, at the bottom of the page, you can see a set is closed if it is equal to its closure, and the closure was defined on the lecture before this. And this is equivalent to saying that the complement of that set is open, but that is something that you have to prove. It's the first exercise in the problem set. Okay, I have more definitions. Compactness equivalent to closed and bounded. Yes, it's an equivalence, but it is tricky to prove. It will take us at least an hour next time to prove this theorem. And in more general spaces, the answer is no. And part of the reason is that in other spaces, boundedness might not even make sense. Yes, we have one more 2-hour lecture on topology where we'll just finish this thing. Yes, sorry, this Thursday, this week. And the last chapter is combinatorics.